In this video, I'll be discussing rate law and how you can experimentally derive rate law for a reaction. So let's take this generic reaction up here. A plus B goes to C plus D. Let's look at what the generic rate law would look like for this reaction. So this here would be the generic rate law for this reaction. And it's going to be rate is equal to K, which is the rate constant. This is something new we're introducing here, the rate constant K, times the concentration of your first reactant raised to an X power, multiplied by the concentration of your next reactant raised to the Y power. And you would keep going for however many reactants you have. So in this case we only have two reactants, so we have A and B. If you only had one reactant, you would just have A to the X. It just depends on how many reactants you have in your reaction. But these things right here, X and Y, are going to be of particular interest to us because these are called the rate orders. And the rate orders are going to determine which of your reactants plays a bigger role in how your reaction progresses forward as far as kinetics is concerned. So we want to experimentally solve for what these rate orders are. And to do that, we need a series of experimental data in order to calculate X, Y, and however many other exponents you have in your rate law. Okay, so let's look at this example up here, where we have this reaction H2 plus I2 goes to 2HI, and we have our generic rate law here. And then down here we have a table of experimental data, where we have the concentration of H2, the concentration of I2, and the rate of this reaction. And ultimately what we want to do now is we want to solve for these rate orders X and Y. That way we can complete our experimental rate law. So you have a generic rate law and you have an experimental rate law. And the experimental rate law is where you solve for the rate orders X, Y, and however many other variables you have in your rate law. So what you want to do is you ultimately want to plug in concentrations for H2 and I2 and plug in a rate given from these experimental data. So we have 3 experiments, and it makes it a lot easier when things cancel, because ultimately what you'll do is you'll divide one experiment by the other, and I'll show you what I mean by that in just a second. But we want to see where things cancel, because we want to solve for each of these variables at a time. So let's say we wanted to solve for X first. To solve for X, we would want to see where 2 of these I2 values cancel, because I2 is associated with the Y variable. So it looks like experiment 2 and experiment 3 allow for Y to be canceled out, because the I2 concentrations are the same, and that would allow us to keep the H2s separate. That way we can solve for them. Let's go ahead and set that up and see what that looks like. So what you'll do is you'll take rate 3 and write it out in the rate law, and then rate 2 for experiment 2 and write it out in the rate law here. So up here we have the data from experiment 3, down here we have the data for experiment 2. And you can see this allows us to cancel K, because K is the same on the top and the bottom, and we can cancel these 2 terms because they're the exact same. So we only have to worry about solving for the X now, which is what we wanted to do in the first place. We didn't want to have to deal with 2 variables at the same time. Now we're just down to X. So now we can rewrite this and start getting a little simplified in order to solve for that X. And to do that, what you'll want to do is divide these 2, so divide 9.6 times 10 to the negative 2 by 4.8 times 10 to the negative 2, and divide this by this. Don't worry about the X yet. You definitely want to keep it in the exponent, but just divide these like the exponent wasn't there, and get what your answer is for that, and then that. So once you do that and take away your canceled out terms, this divides as 2, and this divides as 2, and remember you keep that X in the exponent. So you end up with 2 is equal to 2 to the X. Now this is where you can kind of reach a fork in the road, so to speak. Common sense should tell you that 2 is equal to 2 raised to the first power. So that means x has to be 1, because 2 to the 1 is just 2. However, not all data works out so cleanly. There will be times, or there may be times, where you have to take the natural log of both sides of this reaction, because natural log is how you deal with exponential functions. So to get that x out of the exponent, what you would have to do is take the natural log of both sides. And the rule with natural logarithms is once you take the natural logarithm of an exponential function, it brings that variable down and multiplies it by the natural log of whatever your base number is. So in this case, our base number was 2. Therefore, if you take the natural log of 2 to the x, it becomes the natural log of 2 times x. And then you just divide them out. Like so. And of course, natural log of 2 divided by natural log of 2 is just 1. So, just like we said before, using our sort of deduction skills, x has to be equal to 1. So we'll go ahead and write that up here, x. So the rate order for H2 is going to be 1. So we'll replace this later, we'll replace that x with a 1. Now we need to go through and do the same thing, except we need to solve for y. And if you want to, go ahead and pause the video and look for experimental data which would allow us to solve for y. And then you can check and see in a few seconds if what you did is actually right. So if you were peeking closely, you would know that experiment 3 and experiment 1 would be pretty good to use to solve for y, because we can cancel the x's out. So the k's cancel, of course, the x's cancel. So we're left with the y's over here, and we're left with this term over here. Just like you did before, divide this out, carry the y in your exponent. Let's see what we end up with. So you'll end up with 4 when you divide that, equals 2 once you divide that, and then carry the y down. Now this one, again, pretty simple. You can use your common sense to decide that 2 to the second power equals 4, because 2 squared equals 4. Therefore, y has to equal 2. But if you wanted to do the natural logarithm thing just to check, by all means, you can feel free to do that. You'll have to use the natural log if these numbers don't work out cleanly like this. So it might be a good idea to get some practice with working with those natural logarithms. In any case, we can definitely say that y is equal to 2. Which means when we write the experimental rate law in just a second, we'll replace that y exponent with a 2. Now this right here, it would be your experimental rate law. And we've plugged in those exponents 1 and 2 for x and y. And we can use this experimental rate law to derive ultimately our rate constant right here, k. Now just note that k is going to change for every new reaction that you do this for. K is constant for this particular reaction, but it's not constant for every reaction. It does change, and you do have to calculate it for each reaction that you do. And we'll do that in just a second. But before we calculate k, another thing we can do with the experimental rate law is calculate the reaction order, the overall reaction order. And that's just going to be where you add your exponents for your rate orders together. So individually, 1 and 2 would be the rate orders for these reactants. I2 has a rate order of 2, and H2 has a rate order of 1. That means experimentally, I2 is going to affect the reaction much more than H2 as far as kinetics is concerned. But if you wanted to calculate the reaction order, you simply add these two exponents together. So 1 plus 2 is 3, and that's going to be the reaction order for this particular reaction. Therefore, we would call this a third order reaction. Again, just adding those exponents up. Now let's go ahead and calculate the rate constant k. So to calculate k, just pick any experiment from this list that you want and plug in the numbers for rate and the concentrations. So to make it easy, let's just go with experiment 1, and we're going to plug in all the numbers into our experimental rate law, and then solve for that little k, the constant. So like I said, you just take the data from experiment 1, plug it into your experimental rate law. One thing I will say though, make sure you're careful with your units. Remember, units for rate are molar per second, and we got molar concentration as our units for our concentrations. Units are very important because your K constant is going to have units with it, and your units are going to change depending on what your particular rate orders are. So always make sure you include your units and carry your units to the very end, because if you don't include units with your K constant, your answer is going to be wrong, because they absolutely have units. So you square this number here, multiply it by this number, and then divide over to the other side. So this right here is what you get after you square this number here and you multiply it by this number here. You end up with 1.2 times 10 to the negative 11. And our units here are going to be molar cubed, because if you take this m here and you square it, you end up with m squared, and then multiply it by another m over here, that leaves you with m cubed. So definitely make sure you're including that when you do your math. You've got to carry your units over. So now that you divide it over, of course you'll divide the 2.4 and the 1.2. You'll divide that number out. But another thing you need to keep in mind is your units, how they're going to cancel. So if we have an m in the numerator and m cubed in the denominator, we're going to cancel one of those m's, and we're left with our units that I'll write when we write our answer out. So go ahead and divide those numbers, and then I'll show you what the units end up being at the end. So for your answer, you should get 2.0 times 10 to the 9. And then your units are going to be 1 over molar squared times s. And that's because your m canceled up top, and you're left with 2 m's, or m squared, in the bottom. So you can also write that unit as m to the negative 2 times s to the negative 1. Either one works. You can write it as a fraction, or you can write it in exponential form. But that's how you would solve for the rate constant k. So this number right here is our rate constant.